Is involved, as far as I'm sure everyone knows, in interstellar flight. By any normal meaning of travel, we're going to have to circumvent the intervening distance between points A and B. Relativistic flight, there's the slow boat proposals. We don't normally think of something that takes many generations and 10,000 years as travel. There's the relativistic flights, which have their own problems with resources, power, and whatnot. A lot of these problems that come with even relativistic flight, assuming we could do it, not only present large hurdles, but many of these problems compounding each other. The visions of success that we might use for that include warp drive, which is generally regarded as distortion of space-time. And then there is the jump gate, which is a shortcut that doesn't go through space-time at all, bypasses it. Now, these approaches that try to explore shortcuts, either warp or completely circumventing through hyperspace or some other artistic trick, there's proposals and serious research being done on that, but according to the well-established rules for project success, the management science discipline, these would be considered kind of unproductive and just on their own. And that would especially be the case if we knew that physics was in need of revolution, which we have known officially and has been an official policy since this report came out in 2001, Quantum Universe Committee report, where they said that to resolve all the difficulties in physics that we face, the anomalous observations that we have, we will require a revolution, and they say in particle physics as dramatic as anything that has come before. This would include things like Copernicus and Darwin, which are as big as they get. 2 years later, the National Science Board, who was responsible for figuring out what to do about this report, that a major revolution was needed, came out with this. They said the National Science Foundation should work to support revolutionary, they called it transformative research for political reasons, because if you go to Washington and talk about revolutions, people's faces go white. I had this experience at a breakfast table with a couple of diplomats. Revolutions in science and revolutionary paradigm change is not very well understood generally. And there's exceptions that we're going to talk about. But in the mainstream of science and for our interest, physics research, this report clarified that by stating that revolutionized science by overthrowing entrenched paradigms and generating new ones. Over the next 4 years, the National Science Foundation started implementing that policy that was directed by the board, and they came up with some recommendations. You can see this off their website. Primarily, these were changes into what's called their review merit criteria, which is how scientists get together, they look at incoming proposals, and they decide, well, what kind of merit does it have? And the transformative potential was added to that, but it wasn't clearly defined. This was a problem. Now, the first step in dealing with a problem is identifying it. And our problem is not this. It's not inattention. It's lack of knowledge about specifically what we're dealing with. So, to work on that and to identify what kind of revolution we need, we have to look at the past. And this guy, James Burke, historian of science, he says that the reason we have to look at the past, there's two reasons. One is because the future hasn't happened yet, so there's no place else to look. The second is that the future is just today with extra bits added onto it. What you do tomorrow is just going to be where you are today, plus some things that happened in the last 24 hours. So we will look to the past, and we'll look at people before their revolutions, before the revolutions of Darwin and Copernicus, to see how did they get to the crisis state that led to the revolution, how it compares to ours, and we'll see what we can learn from them that would help us. Okay, we're going to do R&D. Since the historians have done all the research and development necessary for rigorous planning, we're going to call ours rip off and duplicate. We're going to rip off what these historians and philosophers of science have learned about revolutionary paradigm change, and we're going to duplicate it for our situation given what is known. Okay, where did we get our cosmological model from? This is the model, this is the genesis of our cosmological model from Genesis, the Torah. Yahweh separated the waters below from the waters above with a firmament. This is a crystal sphere through which we can see, and then they looked around and they made very reasonable estimations of what their world was. This explains a huge amount. It explains why the sky is blue. It's because the crystal sphere shows the water on the other side. It explains why you dig a well. It explains, well, lots of things. After a few hundred years, we have this, which is a much more advanced, this is a pre-Copernican model. Here, the spheres now go completely around a globe, and the spheres have their different layers. They govern the different celestial objects that we see. But as they made more and more careful observations about this, they started to have problems. And when you have problems with what you observe, you do what worked before, and they added more spheres. So they started adding spheres on top of spheres, and I'm guessing most people in here know what retrograde motion is, but over the course of nights when planets are moving through the sky, they seem to go backwards for a few nights, and then they go forward again because of our relative positions. But there's another way to explain that, which is what they did. They put the planets in a little mini-circle so they could still be going around the Earth, but they just appeared to go backwards on this little mini-circle. That's called an epicycle. And the closer they measured things, the more of these they had to add. And by the time they were done, they had over 50 of these things. And circular calculations, they didn't have quaternions or anything like that. They're doing circular calculations on that with 50 simultaneous rotating spheres, which they had to do to figure out what date it is. Nobody could agree on an answer. Even the same guy doing the same calculations about what day it was, he would get a different answer. The Pope finally had enough. Anyway, this is actually what that looked like. This is for two objects. It was this complicated. And people started looking at that and said, that's ridiculous. That's more confused than the problem we were trying to solve. It makes less sense. This kind of complexity that gets more and more leads to what is called a crisis, identified by Thomas Kuhn in 1963 in his book, The Structure of Scientific Revolutions, which sort of led this, led to the development of this little subspecies of study within humanities departments, the history and philosophy of scientific revolutions. There's also a cognitive science study of this. Okay, here is the pre-dawn Darwin myth. There's God up in the corner creating species. And what they did is the naturalists started noticing the more they measured and the more they identified species, like plants and birds and such, the more creation events that they had to add. And pretty soon they had thousands of these things, and people were wondering, well, look, do you have to have a separate creation for different varieties, and how different do they have to be? And all these thousands of things, they started saying, this makes less sense than the question. They're just different birds. And we can just leave it at that. Or why not? Physics is in the same state. We have zillions of particles, properties. Whenever something weird is observed, there's a new dimension postulated, there's a new force, a new mass, a new virtuon. You can call it whatever you like. My favorite was the postulated particle was the crouton, which accounts for the crunchiness of salads. Okay, where did we get our geometry from? There was a rich kid who was looking for good times, and he decided his parents were going to send him on a tour. He decided to go to the place that had the most regular good times and drug orgies, and he went to Egypt. His name was Thales of Miletus. He went there, and between all these parties, he got trained in geometry, which they had. This was originally developed along the Nile so that after the floods, everybody could put their fields back where they'd been before, because you don't want your farmers killing each other over that. Now, what Thales did after he got back home was he said, look, we don't need to, this geometry is super useful. We don't just need to use it, because by this time the Egyptians had gotten their fields all straightened out and they were building pyramids and laying out cities with cool patterns. What Thales did was he said, you know, we can do all sorts of things. He's most famous for figuring out how far from shore a ship was by using triangulation. And what Thales did, and why he's remembered thousands of years later, was he took the logic of Greece and the geometry for measuring the physical world of the Egyptians, and he put them together and kind of invented our modern rationalist view that reality is logical, and it has logical explanations for things. Okay, so our current theory is based on, we get all these observations, and we're seeing things that we don't understand. So we add what we know based on the model we inherited from the Egyptians, which is based on like 3 spatial dimensions, 1 dimension of time. And one thing I want to mention is that these are what the priests in ancient Egypt told their pharaoh. When you ask a physicist today, what's time? Well, there's a lot of debate. The Perimeter Institute even had a contest about this, where they, you know, send in your essay on what is time. And so we don't know, other than it's what a clock measures. Well, that's what the priests would have said 10,000 years ago. What is distance? Well, they would have said it's a cubit, you know, this length of an arm, that's distance. And that's 10,000 years for about the same is somewhat problematic, and it's led to things like this. I think everyone knows that in another universe, I am not Captain America. Okay, now how can we make some intelligent guesses about what scientific revolutions are? All these problems are fine to say, you know, well, we've definitely got this problem and we haven't shown much progress, and from the addition of dimensions, forces, and these other things that we know in the past that become pretty unlikely, how can we make an intelligent guess? Well, these people who've been working in this field, Nancy in your session, Georgia Tech, this team up in the top left has done very good work, and they've identified what it is that makes a revolutionary change different. And they've even got a criteria that distinguishes those revolutionary changes that they would consider profound, or what they call particularly important. Okay. One of the rules that is not part of that revolutionary study, but general history and philosophy of science has come up with this other thing called the Copernican principle, and it's designed to compensate for the fact that we are biased. When we walk around and we look at things, everything around us, what's at the center? We are. It's because that's where we're observing from, and that's why we're all self-centered in this way. This is the mistake of the pre-Copernicans when they were doing their cosmology. They assumed, quite naturally at the time, that things were as they saw, but they didn't think that it didn't occur to them to think from another position. And the Copernican principle, to combat that, says that if an idea is going to be good science, you cannot assume any special status for humans, for human observers. You have to be observation neutral. Okay, so we went to a paradigm shift from being at the center to orbiting around the sun, a change of position. We corrected that. Now, this change you see also in Darwin. On the left, this is the schematic of it's not even a tree of life, But this is called, on the left, that's called the Great Chain of Being. This is where God set up things in their proper place. And so, everybody knows what truffles are. Okay, truffles. And yeah, we love truffles, all right. So, you know, but they're down in the dirt with the rocks. And the explanation for this was that God put them there because they were in this chain of importance that went from rocks to God and heavenly creatures. And so there was this idea that everything was in its place. And then they had a little side note. There were some people who were saying, well, maybe some small changes should be allowed. Like maybe a truffle could work its way up to a mushroom if it was really an ambitious truffle. And you know, godly people could, you know, ascend or whatever. Anyway, so there's the human though, oh, I guess that's the Virgin Mary there, and then there's people, and down below you see the little monkey. Okay, in the change, now humans are a tiny little, obscure, hardly even a leaf on a gigantic tree. In this one, there's no special place. And in fact, if you were looking at us, you would say very non-special. This is one of the key components. There's a recategorization. To fundamental revolutionary paradigm change, there's a recategorization characteristic. There's a dynamic that occurs where things that you take to be examples of why your paradigm is correct and what you use to even teach it, that it means something different than you thought it was, and it's characterized and thought of in a way that is impossible in the previous system. This gets kind of detailed. One thing that I want to say about this is that these structures seem to these diagrams here reflect what seems to go on in our brains, because these structures are super efficient at type of processing where you only have a little bit of information. Like if there's a furry, curved something out here, like moving like this, all you can see is like some hair and some curvy moving thing, and your brain says dog. And that's super efficient because we almost never have all the data that we need, and why should we anyway? We don't need it. It serves no purpose. So save the brain space. We evolve for efficiency. Okay, now our epicycles, the basis of our cosmology is these dimensions, which they keep adding. You know, every week you're going to see something. If you follow this, you'll see some announcement about higher dimensions. And these are postulated. This is the Wikipedia page on fundamental dimensions of physics. These are the kinds of concepts, like those categories on the previous slide, that show how we think about any problem that's presented to us, any anomaly. We couch it in that. Just like if we were in the Great Chain of Being model, or if we were in the pre-Copernican geocentric model. This is how we always think of things. Our dimensional geometry, this is the oldest known reference to it. It's, I want to say, 8,000 years old. They, before the priests were doing these papyrus scribes, they probably were working it out before then. Now, the reason that we kept geometry, and the reason that the people, that Jewish tradition and the Jews in the Torah tradition kept that model, is not because it was a fundamentally accurate model of anything. They kept it because it was useful, it was popular, and they were emotionally attached to it, because that's the way we get with our mental habits. We like things to make sense, and if somebody tries to come up and pull a rug out from under you with that, it's a shock. I still remember laying in my yard as a kid and trying to see if I could feel the motion of the earth, because it just didn't seem right when I heard this idea. Okay, and here's one of my problems. Modern physics says that the followers of the jackal-headed god of the underworld were basically right in their cosmology. If our dimensions, if our three spatial dimensions and one-time dimensions are correct, this guy's followers were correct 10,000 years ago. I don't believe it. What we need to contradict that model. One of the things that strikes me as very unusual is that in cosmology and fundamental physics, they give our dimensions as n dimensions, capital N, which means what? Integer? Integer dimensions. What percentage of a number line are the integers? It's an asymptote to 0. It's like less than 1% of the line. It's essentially 0 because they're points on the line. And we know that there's nothing in nature that we have ever seen in the history of history that is a point, a line, a plane, a cube. We've never seen those. We make approximations on our buildings because that's structurally sound. But nature never does. There is no such thing like this in nature. There's no reason to think Euclidean-style geometry is good for that. It's the most advanced, useful thing that we've ever come up with, and basing all our physics on it is the best that we've ever done. But for this, modeling the fundamentals of reality, it's not suitable. What we have to do is break out from this paradigm shifts, which we've covered. What we need to do is we need to assume that our perceptions of 3 dimensions of space and 1 dimension of time are similar to the way we see the sun coming up every morning. It's an observation, and I sent that to the Perimeter Institute on their What is Time essay thing, and I got nowhere. I said, look, what time is it's an observation, and we have to step back and address reality humbly. To say that there are 3 dimensions of space and 1 dimension of time is to say that humans are in a privileged dimensional location where we and crickets and mice and fish are tuned in to the fundamental dimensions of the cosmos. And that isn't allowed under the Copernican principle. It's useful, the most useful thing ever, but it's still bad science because it violates that rule. We are not allowed any special perspective. Okay, we need to do good science. That's what I'm arguing for. We need to follow the Copernican principle and address these questions humbly. To reach our goal, we want to approach this from a standpoint of we're seeing observations unfold that are processes in areas that we're not privileged to. There's something going on that gives rise to our perceptions of these dimensions. And it's very similar, likely, to our band of perception is with dimensions, is probably very similar to our perception of, let's say, the electromagnetic spectrum. There's a very tiny sliver of the electromagnetic spectrum that is lighting this room and enabling us to see each other. Everything else, and that's 99% of it, more, we don't see. It's invisible to us. And that's very likely our dimensional situation. Okay, I just got emailed this yesterday, a link to this article, which I kind of poo-pooed when I first heard about it because the reporter was talking. This is called a amplitudahedron. Has anybody read about this? It was just in the news like 48 hours ago. And I want to thank the NASA guy who forwarded this to me. Basically, it's not. It looks like the first significant thing. I haven't been able to dive into all the guts of it, but it looks like a step in the right direction. This is like a really beautiful rendition, obviously, of what he's talking about. There's the napkin back version of it, and what they did, and this is one of those keys of, from an outside project management perspective, when you want to tell when a new technique is onto something. The calculations that they're doing right here, I forget how much compressed, but basically they're doing a small set of calculations there that used to cover 900 pages of calculations. What this is doing is this is a plot here of the predicted position of subatomic particles given certain conditions. And this is I don't know how many people here know about Feynman, Richard Feynman and Feynman diagrams. Okay, this is a the most optimal representation of Feynman interactions and Feynman diagrams that they could come up with, and that gets my attention as a project manager for information systems. When somebody does that, and then they ran the sims on this, and it matched the data perfectly to the stuff, to the 900 pages that they had supercomputers working on for years. So it's a step in the right direction. They're still using capital N dimensions and other things, but I was pretty excited when I heard that. If we do this, if we follow the rules for information systems, project management success, which I feel like it's fair to call fundamental physics and information system, if we do that, and we're lucky, and we stay within the bounds of the Copernican principle, I believe we can usher in a new era of revolutionary physics, transform our world, and hopefully reach the stars. Thank you.
Questions for Bob? Thank you for that journey, by the way.
Go ahead, and then Joe.
Okay. You were talking about the special conditions that we have within the sliver of the EM spectrum that all experiments show here. I thought about that before, and as an extension of that idea, could it be that these kind of Goldilocks conditions have just been around so long, and that's how we evolved to perceive within this sliver?
Did everyone hear the question? Okay. The question is it possible that the Goldilocks condition that allowed us to arise have what?
That's the reason of why we're able to experience each other in this sort of...
Is that the reason that we're able to experience the reality that we do?
Right, that we evolved inside of that.
Yeah, I think that's entirely the case, and I think it's the foundation. I think that's a fundamental fact that will be appreciated in whatever the new resolution to this physics revolution that they say is necessary. Whatever resolves that will have that as kind of like a core starting point, and saying, and after it's realized, people will say, just like we say now, well, of course it's that way. People will say, well, of course we perceive the world this way because we're in this overlapping area that gives rise to these phenomena or produces these processes which we perceive this way. And when you think about it that way, it doesn't mean any of our theories are wrong. It's like the sun still comes up at the same time, only we know it doesn't really come up.
Right. And so is it that another nexus might be the key to interstellar travel?
Well, and this is one of the things I'm going to take my own medicine, is I don't feel it's good to speculate because I'll bias myself. And I mean, I'm already biased enough. I want to see that starship. I want that. But I have to enforce rules on myself to contain my enthusiasm. Yes?
Why is it that we need to take the Copernican principle as foundational for physics as opposed to a really interesting philosophical concept? What if reality is that there is a very privileged position I just don't understand.
We don't have to, and it could be the case that humans are in a special privileged place, but for all the revolutions for which we have evidence, that's not been the case, and the removal of humans from that has been key. And the other thing is, it's natural for us to make that mistake. So we don't have to do it, but it's a best practice.
So you're going to put this pitch on your video channel?
Beg pardon?
Are you going to put your pitch on the video channel you have?
Somebody who's heard of it.
Well, I just looked it up.
Probably.
That would be good because you've raced through, a number of good points but it's hard to, you know, find those things later. You can't
I get that complaint with the blog a lot too.
Yeah. So, yeah. My suggestion is you just play the charts on your computer, record it, and then upload it.
All right.
Any other comments for Bob?
One last, I'm sorry, it's stuck in my mind.
Sure.
Is there some sort of methodology for testing, like, you know, sliding along those different nexuses, let's say, of, you know, the EM spectrum, I don't know, any of the variables that you see being able to...
Yeah, the question is really about, is there a reliable methodology we could point to test this idea? And actually, I would say not really. What you want to do is you want to generate hypotheses and then start, and what you need to do, like, I actually made the case, if we were building a starship, how would we do it? Like, if someone hired me and said, look, you have to deliver in 15 years, you have to deliver a theory that would enable faster than light transit. And if you do, you'll get a $10 million bonus. In project management, you get bonuses for delivering things on time. And so they said, look, we're going to make you really rich if you do this. And what I would do is I would say, okay, here's what we have to do, is generate the best ideas for physical models we can do, and they have to be testable. Because if you can't test them and you can't throw them out, then you just got a mess, and you can't do everything. So what you do is you put forward researchers to develop those models, and you prioritize them based on Occam's razor, which is the simplest, like those guys came up with that simple amplitudahedron, 900 pages down to this geometric structure that does calculations like that. And they're right, they're correct. These guys will probably get a Nobel for it. You need that type of criteria so that you can decide, because look at this conference, there's 200 approaches here, and everybody wants warp drive. I mean, does anybody not want warp drive? We could have it. Okay, so it's unanimous. So, and everybody, you know, everybody's going to come up with ideas, and some of the ideas will be crazy. Some of them will be crazy and good, some will be crazy bad, some will be like very, you know, you get everything. You have to be able to screen them. And so, like this, applying Occam's razor, where the simplest explanation, you work toward that. But the other thing that you have to have is it has to be testable. It has to be falsifiable. So you can do an experiment. Now, if I could just take a quick minute. Okay, everybody heard about falsifiability in testing scientific theories? Anybody who has not? Okay, so if you get a negative result, and Feynman famously said this, if you give a negative result, it doesn't matter how beautiful or popular your theory is, it's wrong. Let me tell you about Copernicus. He came up with this idea. He said the Earth moves, it goes around the sun, and it's got this gigantic orbit that's so big we can't feel it. Another interesting side note, he was trying to save astrology. That was the prime motivation, although the Pope was paying for calendar movements. Anyway, so the skeptics who said, look, you and I are not whizzing around at thousands of miles per hour. That is crazy. And we feel nothing? That's crazy. And the sun doesn't come up? That's crazy. But let's assume, for some reason, all these crazy things could be true. There would be a way we could tell. Because if we're orbiting like this, then what we could do is we could look at the stars and we would see them shift over the course of 6 months, going these zillions of miles from one side of the planet to the other. And if that happens, then you're right. And they did the experiment, and they saw no change at all. The theory was falsified, according to the classical formulation. Did they change their mind? No. They changed the goalposts. They said, oh, it's not because our theory is wrong, it's just because the stars. Yeah, the stars are too far away. That's it. And they turned out to be right, but it was just a crazy, save their ass kind of move. So on that, on that happy note, thank you very much.